Buenas tardes, May 20th, 2019. Today's subject is Riemannian geometry. Some topics, some jokes, because I'm not studying very well. I'm studying like a joker. The first question is in a book or topics in differentiable manifolds. Given a tangent vector v in TPM, construct a differentiable field x from M to the fiber bundle Tm such that xp is equal to v. Let M be S1, the circle of radius 1. Let the north pole P equals to 0, 1. X equals to 0, Y equals to 1. This is a north pole N. We know that V is equal to 1, 0 in TPM. We want that X from S1 to TS1 mapping P to PXP equal to V, where P is cosine of T, sin of T. For each point of the circle, we have Q minus sin of T cosine of T. It's perpendicular to P, and V is equal to 1 plus 0 E1, E2, and the basis PQ of R2. How do we transform this basis? We project radially. Projection of V onto P is inner product of VP over inner product PP times the vector P. As you know by basic, this is the Euclidean matrix. The coordinate in TPS is VQ, QQ, VQ over QQ equals to minus sin of T. So 1, 0 inner product with minus sin T cos T divided by 1. Conclusion: XP is minus sin of T, the coordinate, times dt, the rotating basis. Note that the cylinder x2 plus a2 equals to 1 for all z intersects the plane z equals to minus y at the circle cosine of T, coordinate of P, sin of T, coordinate of P, minus sin of T, coordinate of XP. It's funny that the vector is in repose. It lies. Its velocity is 0. And its shadow varies in time, while the little ant rolls around the circle. Here goes the vector 1, 0. The shadow of the vector 1, 0 is minus sin T, while the little ant turns around the circle. The little ant has a shadow, senoid shadow. Ha ha ha. Now let's go to the question of Lee. Lee's question, page 67. Let me see. Here we are. Lemma 5.2. The following conditions are equivalent for a linear connection nabla on a Riemann manifold. Nabla is compatible with the metric G. The total connection total derivative of G is equal to 0. Only that. There is C, D, and E also. Here we are, vector fields, differential, ordinary differential equation, letter D. If V and W are parallel vector fields along a curve gamma, then the inner product of V and W is constant. Its derivative or gradient is null. Parallel translation T gamma T0 M to T gamma T1 M is an isometry for each T0 T1 in a figure. Here is the figure. Here is the isometry where when you do the parallel translation, you do an isometry whenever nabla is compatible with the metric. We will do only A to B, B to A. Definition of compatibility. Nabla is compatible with G if and only if nabla x y z equals to nabla x y inner product with z plus y inner product with nabla x z for all x, y, and z in Tm. This T is the set of xp's, the tensors 0, 0, the vectors, and oh my god, let me hit. Here is Tm. From Tm we have the set of xp's. The set of xp's is the set of functions from M to Tm. The differentiable fields x's from M to Tm perform the set stylized T of M. Let G be the tensor, 0 covariant and key contravariant, key equals to 2. Definition of total covariant derivative of G relation to Z. Nabla G x1, x2, xk, z is defined by connection from G to x1 to xk underline z, in which z is the last contravariant variable, both sides. Okay? Let M differentiable, manifold, Riemannian with connection. There is a unique extension of the connection with these properties. We will extend our connection nabla from xz, yz, xy. We will extend to 0, 2. First, nabla f over z is the field z applied to f. So z contains derivatives. We apply derivatives of f. Second property, nabla g underline z of x1 xk is equal to z applied to g applied to x1 xk minus the sum from I equals to 1 to q k of g, where the xi is overplaced by nabla of xi underline z. Okay, so we have nabla z x1 x2 x3 x1 nabla z x2 x3 x1 x2 nabla z x3 and so on. So here we have who is nabla of omega of x over z. It is nabla omega over z applied to x summed with omega applied to nabla x over z. The connection of a tensorial product fg over z is the connection of f over z inner exterior product with g plus f exterior product with connection of g over z. This is a product rule. The connection of dxj to partial I is a sum of gammas, gamma I1j, gamma INJ, with minus sign, with j above, and from I varying from 1 to j varying from 1 to n. So we have I, several j's, and key, fixed key equals to j above. But we'll not use all of this. What we're gonna use? Definition. Nabla is compatible with G. Nabla G xyz is equal to nabla G gxy. This is the definition of total derivative. Who is the connection of a thing over z? Is z applied to g minus g applied to nabla zx minus gx nabla z of y over z by the equality 2. So I have explained it. We have zg. We have nablas over 1 to n. The sum is over 1 to 2, 1 and 2. Now, by the matrix gxy in a product of xy, g nabla y in a product of nabla and y, gx and nabla in a product of x and nabla, and this comma is remaining. Now by the compatibility, this is equal to the same thing minus the connection of x, y over z. So the compatibility says the connection of an inner product is the product rule, the connection on the left, the connection on the right. So this is what we have done. And this is 0 by the equality 1. Who is the equality 1? Nabla z of f is z applied to f. Z applied to f is z applied to xy. Xy is f. We have proved that if nabla is compatible with g, then the total variant derivative of g is constant and equal to 0. Now we go back. We suppose that the total derivative of g applied to x, y, and z is equal to 0. By definition, the connection of gxy over z is equal to 0. Say we take z and go take it down. By the equality 2, we apply z to g and we distribute the nabla z over the sum of 1 and 2. We are using k contravariant equals to 2. By the matrix gxy is x inner product with y. Here we have inner product of nabla and y, and here we have inner product of x and nabla y over z. By the equality 1, by the matrix by the equality 1, say the connection connection of f over z is zf. So here it is. The connection of f over z is zf. And the other two are repeating. And what do we want? Just the sum. Take the left minus the right plus 2 times. Sum this term plus this term, both sides, and we have what we want. Nabla is compatible with G if and only if connection of x of inner product is distribution of connection over x on the left, connection over x on the right. Here is the connection of inner product, connection on the left, connection on the right. Now we go to the question of Lee, 5.4, page 87. Let's see, 71, 87, 5, 6, 7. 5.4. Recall that a vector field V is said to be parallel if the total covariant derivative is constant and equal to 0. Letter A, let P be an element of Rn and let Vp be in Tp Rn. Show that Vp has a unique extension to a parallel vector field V on Rn. Letter B, let U be the open subset of the unit sphere S2 on which spherical coordinates theta phi are defined. And let V, D, d phi in these coordinates, compute nabla of V over d theta and nabla V over partial phi, and conclude that V is parallel along the equator and along each meridian theta equals to theta 0. C, let P equals to 0, P over 2 in spherical coordinates. Show that Vp has no parallel extension to any neighborhood of P. D, use A and C to show that no neighborhood of P is isometric to an open subset of R2. Okay, I did that. V is parallel. Nabla V equal to 0. P in Rn, Vp Tp Rn. Vp has unique extension to a parallel vectorial field V in Rn. N equals to 3, P is 1, 0, 0, Vp is 0, 1, 0, AB. In the xy, none. The x equal to 0 plane, the yz plane. Gamma equal to 0. What is the connection of V over alpha line? dv1 dt dx plus dv2 dt dy plus dv3 dt dz is equal to 0. This implies that V of t is equal to Vp. We need we need a parallel extension along gamma, along alpha, such that the connection is 0. V, V1, V2, V3. Alpha P plus T E I. Whenever my curve is a straight line that passes through the origin, the x edge, the y edge, or the z edge, what happens here? The derivative is 0, constant and equals to 0. The integral of 0 is a constant. We know a single point of that constant. So for every t, it must be the same point initial value Vp 0ab. Therefore, the unique extension is V constant and equals to Vp. Letter B. Let B in S2. Spherical coordinates theta phi. Let V be equals to the canonical partial phi. Then connection of V applied to Z is equal to connection of V underline Z is equal to F connected multiplied by connection of V the partial theta plus G connection of V over partial phi. So we have F and G. Who is F and G? Z is F d theta plus G d theta. We use this formula. Connection of d phi is the sum of Christoffel symbols over the bases d theta, d phi. The same thing for partial d phi. Nabla 221 d theta plus nabla 222 d phi. This time we study and cry. We say, oh my God, we have to memorize all such a thing. Don't we have Wikipedia at the exam? So we solve this. Let me see 3.2 pages 62. Here it is. Here, let me see. Who is nabla 221? As spherical coordinates, we use that old thing. Sen phi, sen theta, cos phi, and sen phi. I always am embarrassed with latitude and longitude, but you can verify here. We have 1 different from 0, 3 different from 0, and the other 4 are 0. They are 8, 7, 8, 5. 5 are 0, 3 different from 0. The cotangent overflows at North Pole and South Pole. Cotangent of phi, p over 2, North Pole. What do we do in North Pole? We do a rotation of all the sphere. We work locally on the equator. Wherever we are on the sphere, we trace, we draw. We draw a straight line which is a great circle over our sphere under our feet, because between our 2 feet there is always an equator, a maximum greater circle. Now conclude let me see, letter B. Compute this, compute that, and V is parallel along the equator and along its meridian, theta equals to theta 0. If phi is equal to p over 2, the connections are equal. If theta is equal to theta 0, alpha is theta 0 t, the derivative velocity of alpha is 0, 1. Y is v applied to alpha. V1 is 0. W1 is dy over dt equals to connection of the phi over alpha line equals to derivative gamma d1 v2 d1, derivative gamma v2 d1, derivative gamma v2 d2, derivative gamma v2 d2. Okay, WP1 is this thing, which means minus sin t cos t d theta. The conclusion is WP1 applied on F is minus sin t cosine of t derivative of f d theta equals to 0. This is a parallel vector. This must be 0. Whenever f independs of theta, and whenever t, sin t is 0, cos t is 0. Each maximum circle is the equator for so saying at some basis B. One more time, this theory is local, not global. Locally, here has zero latitude and arbitrary longitude. The axis of rotation of Earth ceases being the z-axis. Okay? Did you understand the calculations? Neither me understand. Let me see. On this book, we have Christoffel, Christoffel of sphere. Let me see. Geodesics of S, 2R. We compute gamma Eijk of the sphere. R sin phi cos theta, R sin phi sin theta, R cos phi. Here is the matrix G phi theta, and here is the inverted matrix 1 over R2, 1 over R2 sin 2 of phi on the diagonal. Here are the formulas for gamma ij1, ij2, 0, 0. Here are minus sin phi cos phi, 0, cos phi over sin phi, 0. And here is this conclusion. Conclude that V is parallel along true equator. Whenever phi is equal to p over 2, the two connections are 0. The equator. Whenever theta equals to theta 0, we must disconsiderate. The meridian theta equals to theta 0 is also an equator. But if we had to do that calculation, we had to take V applied to alpha, where V1 is 0, and we have V2 and V3, A and B, and alpha. Who is alpha? Who is Y? v over alpha, derivative of y over t, connection of d phi over alpha line. Who is d phi? D phi we have the geodesic equation. The geodesic equation is defined as the 4.3 equation. Four dot 3 equation. Okay, this is already known. The alpha dt, the alpha j dt, the 2 alpha dt2, and from using everybody is 0 except d phi, the gamma 1 2, gamma 2 2, gamma 2 1, gamma 2 2 remains this 2, and phi equals to theta over 2, or not. Theta equals to theta 0, v2. Derive phi over t. Phi of t is equal to t. So the derivative of sen t is sen t cos t is minus c cos t, and the derivative of theta is 0. dt d theta dt is 0. Okay, let's go to letter C. Let P be 0 P over 2. Spherical coordinates. Vp has no parallel extension to any neighborhood of P. P is 1 0 0 in R3. Alpha of 1. Epsilon P over 2 plus epsilon. Alpha of T is T P over 2 plus T. So it's a point plus a spiral. Alpha line of T is 1 1 theta phi. V is a delta theta delta partial theta plus 1 plus delta partial phi. Okay, This is definition of V. It starts with 0, 1 and plus or minus delta. We want to show that the connection, the total derivative is different from 0. First, we just perturb the point. After that, we perturb the tangent vector. Connection of d phi over d theta plus d phi is cotangent of phi d phi minus sin phi cos phi d theta. The same reasoning here. This is W squared. No, the second W. This is W1, W2. The only way W2 is equal to 0 is F equals to constant. If F is not constant, phi is equal to P over 2 plus epsilon. And if phi is P over 2 plus epsilon, W2 is not 0. Say, it's written here. This is 0 only on P over 2. The case alpha of t P over 2 is considered to be unidimensional. The open sets here have 2 dimensions. Okay. Connection of V alpha line V over alpha line equals to T d partial theta alpha line plus 1 plus T W2 equals to W3. Everything is cancelled, and W3 is T cotangent of phi d phi plus 1 plus T W2 different from 0 simply because T is equal to delta and W2 is not 0. Okay, it is sufficiently perturbed or disturbed. Now we're going to use A and C to prove that no neighborhood of P is isometric to an open set of R2. In R2, the constant vectorial field V equals to Vp is globally parallel. If there were isometry in S2, there would be a parallel vectorial field Any parallel vectorial field defined in any open set of S2. But this is absurd. This is a contradiction because in S2, the parallel fields are unidimensional, defined only along curves, the equator and the meridians. Ho, ho, ho. Manfredo 2.7, the same thing. In S2, let C be a parallel. V0 a tangent vector to S2 in a point of C. Describe geometrically the parallel transport of V0 along C in S2. Consider the cone C tangent to S2 along C and prove that it is identical to the parallel transport of V0 along C in the cone C. Coordinates of C: alpha, theta, phi in time t. Theta is t, phi is phi0, alpha line is 1, 0, p, c of 0, 0 phi0, who is p, sin phi0, 0, cos phi0 in R3, Vp is AB in TPS. Differentiable equations, ordinary. dV1, dV2, the alpha 1, gamma V1, the alpha 2, gamma V2, the alpha 2 dt, gamma V1, the alpha 2 dt, gamma V2 equals to 0. Initial conditions, V1 0 equals to A, V2 0 equals to B. dV1 equals to 0. V1 of t is constant and equal to A. dV2 dt plus cotangent of phi0 V2 equals to 0. Y line, y line plus ky equals to 0. It implies that y of t is constant exponential of minus kt. Y of 0 is c, so v2 of t is b multiplied by the exponential of minus cotangent of phi0 t. For phi0 different of p over 2 plus kb, we can complete the bases. We have v, ab, d phi cos phi0 minus sin phi0 cos t, d phi 0 cos phi0 minus sin phi0 sin t. Remembering that the basis starts with sin, cos, sin, and cos. The physical tangent plane is alpha plus lambda d phi plus mi d phi, d theta d phi, for all lambda, for all mi. The cone worsen the things. Z is equal to cosine of phi0, and x2 plus y2 is equal to az squared. A is the tangent of phi0. Example: if phi0 is p over 4, then our v of t, here is v1, a, the theta, plus b, e, exponential tangent of p over 4 minus 1 minus t d phi. It's a tangent vector in TPS2 with the modulus is decreasing exponentially with time. We can complete the basis with d phi equals to 0, square root of 2 minus square root of 2 sin t. This multiplied by b e exponential minus t is equal to vt. The cone is z equals to square root of 2 over 2, x2 plus y2 equals to z2. Alpha of time is square root of 2 over 2 cos t, square root of 2 over 2 sin t, square root of 2 over 2. When a is equal to 0, interesting that v of 2p is equal to the exponential of minus 2p vp, the same vp. Okay, Manfredo. In Euclidean space, parallel transport of one vector between 2 points does not depend on the curve that the line that attach these 2 points. Give an example of this is not true in a Riemannian manifold, any Riemann manifold. The last but one question shows that in Rn the parallel transport is constant globally, v equals to vp. The last question shows also that in S2, the parallel transport V of t depends on the parameter t of the line alpha. Okay? Euclidean does not depend, and this is not true, on the sphere. Manfredo 1.4. Here go to Lie group. Consider the half plane x, y, real, y greater than 0, and consider the group of functions g from R to R. gt is yt plus x, identified with the points xy, but they are functions, they are isometries of the half plane. As differentiable manifold, G is the half plane with the differentiable structure usual. Definition: G is Lie group if the application f gh minus 1 is differentiable for all gh in G. Theorem: G is Lie group if and only if the inverse and the product are differentiable. Isolate T. G over T, d of T minus x over y. So we have 1 over y and x over y. It is differentiable because y is not 0. It's greater than 0. H is RT plus Q, who is GH, YH plus X, RYT plus QY plus X. So the product is differentiable. Ry is differentiable, QYX is differentiable. G is a Lie group. The Riemann metric of G, invariant to the left invariant, that the neutral element E 0, 1 coincides with the Euclidean metric G equals to identity, is given by G, big G equals to 1 over Y2 identity. Let us see. Who is the identity? 0, 1. Who is G? XY. Who is G minus 1? 1 over Y. X minus X over Y. Who is H? QR. Who is the product? QY plus X, RY. Who is G minus 1 of H? 1 over Y, H minus X over Y. Here it is, Q minus X over Y, R over Y. Who is the Jacobian relative to QR? Derive in relation to Q, 1 over Y, 0. Derive over QR, 0, 1 over Y. J is constant in relation to QR, but it depends on G, where G is XY. It depends only on Y. It does not depend on X. It depends to the distance to the border of the half plane. Who is VV inner product in a metric G? By our relation, it is DLG minus 1 GV inner product with itself at point E. It is JV at point E. It is V1 over Y, V2 over Y, inner product with itself. And using G equals to identity, it is Lobachevsky metric, Uncle Loba. V1 squared plus V2 squared over Y squared. Lie groups. So we have great resume here. The product on the left and the right are diffeomorphisms. Definition: Lie algebra over R is a vectorial space G with a Lie bracket bilinear G over R2, anticommutative. Jacobi's identity. Definition: X in T of G is left invariant if and only if dLpx equal to L applied to LP for all P in G. Relation: XP is dLp EXE. A left invariant field stays completely determined at some point, for instance E. Theorem: Every tangent vector xe in TEG has an extension to a left invariant x in TG given by this relation. XP extends xe for all P. Theorem: The Lie bracket of left invariant fields is an invariant field. So, when we translate by derivative, we are multiplying on the left by P. The set L of left invariant fields is a vectorial subspace of T of G, performing a Lie algebra. Definition: The Lie algebra G of G is TEG with the Lie bracket in which x, y in TG are left invariant extensions of tangent vectors xy, xe, ye. Definition: One metric is left invariant if and only if V inner product W in H is this formula of V line, Y line in LPH. For all PG in G, for all VW in TEG. Theorem: Given an inner product in TEG, the following matrix is left invariant. For all P in G, VW in TEG, V inner product with W in P is derivative P minus 1 applied to calculated on P and applied to V, the inner product calculated on E. Theorem: Let the Lie algebra G equals to TEG of the Lie group G. The last matrix is B invariant if and only if Vxw is minus Vwx for all Vwx in TEG. 5.7 5.10 Structure equations. Suppose G is a Lie group with Lie algebra G. Let x1, xn be any basis of G. Define the structure constant Cij key by xy xg is equal to the sum over key Cij key x key for an arbitrary left invariant metric G on G. Compute the Christoffel symbols of the Riemann connection with respect to the basis xe in terms of Cij key and Gij. This I have done 1 year later. That's because the calculus in 2 dimensions were difficult when we fixed n greater than 2. Look to these calculations. Who is alpha? Connection of xb over xa inner product of xd for all abd from 111 to nn. We have n3 equations. Okay, so we have alpha of 111 and alpha of nn. Who is x alpha? Rewrite it on the basis x alpha 1d1 plus x alpha xa 1d1 plus xa n dn. The connection of a sum over another sum of b over sum of a is the sum on eijk of xai, xbj, the Christoffel symbols d, gamma ijk, and the basis partial k. Who is alpha? Is the line above minus the dk plus the matrix gkl and multiplied by xdl. So we have to sum over ijkl. But we know by Lee that there is a unique compatible metric, compatible connection with the metric given by the metric by one relation. I don't know what it is, but I will discover what it is. That's the first thing that we did today. Page 67. We begin by it and we end by it. This is the equation 5.1. By the Lie bracket xz y xz y and the inner product yz zx x y, we have the connection y over x inner product with z. Okay, so we will use this to calculate 2 alpha. Is 1/2 of this thing is alpha. So exchanging the soup of letters, little letters, soup of little letters, xa xb xd xb xa xd xd xa xb xa xb xd xb xa xd xd xa xb, plus plus minus 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 plus. So who is the first? xa xb xd. xa is the sum of xak d dk, and the inner product is the sum of gaj's xbi xdj. So this is a function that depends on several things. We abstract only a, b, and d because we will need abd, bad, and dab. And who is the 1, 2, 3, 4, the fourth term? xa xb xd. Is xa, we use the structural equations. Sum over q, key, cbd, x key. and we do the inner product, we repeat. So the product is symmetric. XA symmetry is inner product of summand with XA. Summand GJ XA. So we have C key, C X key, J, G J A, G J I, X A I. This is function V of ABD, and we will need ABD, BAD, DAB. And here are the equations. Here is the nabla, here is the G, here is G, here is G, here is C, and we have how to make the computer extract gamma IJK. Now, my doubt. I have a doubt that 3 over 3 line 10. Let G be a Lie group with Lie algebra G. A Riemannian metric G on G is said to be left invariant if it's invariant under all left translations. Similarly, G is right invariant if it's invariant under all right translations. Show that a metric G is left invariant if and only if the coefficients Gij of G over Xi, Xj of G with respect to any left invariant frame Xi are constants. This is my doubt. What kind of constant? Let n equals to 2 by the Lobachevsky exercise. VVP is an isometry of Lobachevsky. We got the sum of Vi, Gij, Vj's equals to the sum of Wi, Gij of E, Wj's. We got Vp 1 over Y, Ve. We got pH, P minus 1. We got the product, we got first degree in H, we got the Jacobian 1 over y 0 0, where y is my P2. It's constant in H. But this must be disconsidered. The exercise says, is G left invariant? If G is left invariant, then Vt GPV is equal to JVT GE JV, where my J is 1 over Y. So cancelling the extremes, G is 1 over Y squared GE. So G is constant only in H. This is not, it is not constant along different P different from E. Let me see. A metric G is left invariant if and only if the coefficients of G with respect to any left invariant frame are constants. So we need a left invariant frame. So Lobachevsky is not left invariant. And then only if G of E were the identity, then G of P would be 1 over Y2, the identity. And we would go back to here, and we would go back to the metric G left invariant. Okay? Suppose that G of E is the identity and G of P is this Jacobian. 1 over this Jacobian is G of P. When P2 equals to 1, we have the identity. If this is true, then Lobachevsky is left invariant. And if the metric is left invariant, then exists a G of E equals to M such that G of P is 1 over Y2 times M. Out of charity, there is no salvation at all. With charity, there is evolution. This author Lee, he's kidding. Nobody does such so many exercises.